the system applications. What kind of system are we applying to? We will have motion initially, right? Motion. What kind of motion?
Linear, rotational, vibrational.
Translational motion. In translational motion, we discuss the motion in different scenarios. What are the scenarios? It's a free particle in a box. The box is 1D, 2D, and 3D. Okay. All right. What else do we apply to? In translational motion, this is special case. We talk about it. It's quantum tunneling. Quantum tunneling is also related with translational motion. In this case, we only discussed the in one dimension. Okay, all right. And then we can go into the depth. What are the model? What is the Hamiltonian operator? And so on and so forth. All right. Now, when we do the translational motion, in one dimension, two dimension, we will have a boundary conditions. To satisfy the boundary conditions, we introduce quantum numbers. What are the quantum numbers we introduce? N1, N2, N3. You can go ahead and do it.
Okay, I have to go get IT because it's just locked up, unfortunately.
Yeah, that's what I saw.
Yeah. Would you like them to come over right now?
Yeah, that would be nice.
Okay.
All right. So now, if it's only one dimension, you only need a one quantum number. Satisfy one testable boundary condition. 2D, you have two dimensions, and 3D. So one dimension, you only have one. Two dimension, you have two. Three dimension, you have three quantum numbers. All right. And what else do we apply to? We apply to vibrational motion. Okay, now what kind of a model do we talk about this?
Harmonic oscillator.
We started with very simple harmonic oscillator. Okay, and we can do motion in 1 or 2 and 3 for this specific in one dimension. In what kind of dimension? For the simple harmonic oscillator. I think we only touch bases in one dimension. And then what do? We bridge to we bridge to the diatomic molecule. We assume it's the potential force in diatomic molecules also can be simulated by the potential on the simple harmonic oscillator when the system is near or close to the equivalence point, because the potential energy of this is a parabolic. Okay, now only going to be correct to some extent when you are near the bound length equivalence point. Okay, now to bridge from the simple harmonic to diatomic system, what modification do we use? For the simple harmonic oscillator, you only have 1 point of mass. For diatomic system, I have 2 points of mass. How do we do that? We introduce effective mass. The rest of the are exactly the same. Okay, now what are we going? You guys see where I'm going to? And then recently we talked about rotational motion. We will have a free rotation on the ring. rain, which is a two-dimensional problem, but we said with we constrain it also with the fixed radius. So therefore, from a it is a two-dimensional system, but we reduce the two variable only to one. All right. Now, what else do we have? On the sphere. So basically, if you think about this should involve the r and phi, because you rotate in a two-dimensional system, you could rotate with a larger, a different kind of a radius. But we fix the radius, so we reduce it only to the phi, the 2D angle, right? The two-dimensional angle right here. Now on the sphere, also with a fixed radius. So supposed to be it's a r, zeta, and phi, right? So you can think about this. You can have a stacking of right, so each one of them are rotation on the ring. Now you stack them together, adding the theta angle. That is your rotation on the sphere with no changing radius. So therefore, that's what we discussed. I think that's what we ended from the previous lecture, is how to solve for it. Then once we know the wave function, then we can calculate a lot of those properties. But I'm just giving you guys a model for each of the system. Once you solve for it, know the wave function, know the energy expression, then you can calculate a lot of things, because that's based on the postulates. Once you know the wave function, then you can have all kinds of properties. Okay, now the trick is, how do we know the wave function? And those are the based on the models. Okay, now let's keep going. If we're thinking about electrons in the atom, right? Electron orbit around the atom. You can think about as a rotation So if we have, let's say I have a hydrogen atom, I have a nucleus right here, and I have an electron right here. The electron can orbit. Previously, you guys said it can be 1s, 2s, 2p. That has a different radius. But each of the, you can thinking about it, each of these orbital, you orbit consider as rotation on the sphere. So that's what we're going to bridge into. Finally, after we discuss all of this, we're going to come to our system of our interest, is how do we understand from quantum mechanics point of view of atom and molecule. And the first atomic system we're going to talk about is hydrogen atom, or hydrogen-like atom. Can you guys see this board okay, the color? It's good? Okay, all right. So this is a chapter 8, or topics 8. Okay, so hydrogen atom, or hydrogen, I say hydrogen-like, or you can say hydrogenic atom. Now, what is a hydrogen atom, guys? What constitutes a hydrogen atom?
Proton.
They have proton. What else? Because that's our system. Because we need to define, from quantum mechanics point, we need to define the system. So hydrogen atom is our system. Now, in this system, do we have a single particle, multiple particles?
Two.
Huh? Two particles in the hydrogen atom? Then what are they?
One proton, one electron.
have one photon, you have one electron. Yeah, good. So in an atom, I know hydrogen is the smallest one. In an atom, we will be thinking about you have a nucleus, right, and then you have electrons, right? Yes.
So for this topic, we're not going to include isotopes, is that correct?
Isotope. Pretty soon toward the end of the semester, we would know that quantum mechanics is beautiful, but unfortunately, it has a lot of limitations. Limitations I'm going to show you very soon, because solving for a Schrodinger equation with 9 variables can be, or 10 variables can be very, very challenging. Okay, so but we have to introduce approximation. So basically, the idea is good. Now, how far we can take from quantum mechanics perspective to understand the system, unfortunately, sometimes is constrained. Okay, okay, all right. Now let's get back. So usually in an atom you have a nucleus. In the nucleus you have protons and neutrons, and then you have electrons. Do you guys all agree with that one? Okay, so let's just make it generic. So I will have a nucleus right there. So then we can bridge into other atomic system. Okay, all right. Now, for hydrogen atom, we only have one electron. Do you guys agree? So the hydrogen-like system, we are specifically refer to something that only have one electron. It can be an atom, like a hydrogen atom, or it can be an ion that only have one electron. Can you guys give me some example? We're talking about a hydrogen-like system that is only one electron. All right, now of course, hydrogen atom only a one electron. But I can have atom that lose all the electrons except the one. That is also a hydrogen-like system. Do you guys follow me, okay? Like, give me an example.
Helium plus.
Can I do helium plus ion? That is one electron system too, right? What else? Oh, I can name so many. I can do sodium 10 plus. Sodium has 11 electrons, and then lose 10 of them, make a cation, and then only remains one. So that is all included as the hydrogen and a hydrogen-like system. They're all the same. You guys follow me, okay? Okay, all right, so that definition is clear. Then, in that case, in this particular system, can we come up with the wave function with corresponding variables? Okay, that's the first thing we need to do. Because in order to solve from quantum mechanics perspective, we need solving for the Schrodinger equation. In order to do that, we need to generate the wave function with the correct variables. And then we need to generate the Hamiltonian operator. And then you piece them together in the Schrodinger equation solving for it, you will have a solution, hopefully. Okay, now for this particular hydrogen-like system, we have two types of particles. One is the nucleus, the other one is the electron, one electron. So how many variables would we have? 6. Or we would say, we would have 2 position vectors. One is a position vector, a set of x, y, z, to refer to define the position for the nucleus. And the another position vectors is to refer the electrons. right? Because you have two particles, each particle to define in the space, you need to have a position vector. Now, if it's a motion in three-dimensional space, then each of the position vector would have I use an N to refer to the nucleus. You will have the X, Y, Z component. Then you also have the X, Y, Z to define that electron. And I think that's why you told me 6 variables, right? If you really write out, there are 6 variables. There are axes for the nucleus and the electron, Y, vice versa. There's 6 of them. Now, I'm going to leave this later for you guys to figure it out. Solving for this Schrodinger equation for 6 variables is challenging. All right. So, all right. Now, that is our system. Now, how about our Hamiltonian operator? So we come up with wave function with the variables. How about this Hamiltonian operator? Now we're looking at this system has a nucleus, one electron. Now can we come up with a Hamiltonian operator for this particular system? Now the total Hamiltonian operator always equals to the component of the kinetic energy for the system plus the potential energy. Awesome, thank you. Yes, I will see you on last semester.
No kidding, yeah. See you again.
Yes, okay, thank you so much.
Good thing. Yeah, that's all set.
Yeah. You know what happened is
Looks like this thing here is.
so if we think about this Hamiltonian operator, it has 2 components, the kinetic energy component and the potential energy component. Now we have 2 types of particles in the system. What are they? The nucleus. Oh, that is not the right side. The nucleus. And what else? Electrons. Both of them will have motion in 3-dimensional space. Do you guys agree with that? So therefore, the kinetic energy component, we will have a kinetic energy part to define the nucleus in 3-dimensional space. And then you have the kinetic energy component for that electron. Okay. I mean, it's like you guys in this room, each one of them a particle, you can have a kinetic energy, and then plus the interaction, the potential energy you with the rest of the group. Now, how about the operator thing? How about the potential energy? So we have nucleus right here, and then we have an electron right here. So the nucleus is positively charged. The electron is
Negatively charged.
negatively charged. So it has a Coulomb potential, isn't it? Is that a Coulomb potential? Coulomb potential, right? You guys all agree? Coulomb potential, you have point charges in the field, and then you go, do we talk about Coulomb? We say the potential couldn't be as a result of the position. The potential can also be as a result of the electric field. Okay, so in this case, you have in your system this whole thing. If your hydrogen or hydrogen-like system, then these two will have a Coulomb potential. Now, how are we going to calculate generic expression as a Coulomb potential? We say V equals the generic expression for 2 points of charge. You're looking at me. Tell me what it is. The generic expression.
I'll remember. But it's something like charge 1 times charge 2 over mass and distance squared, probably.
So charge 1 time charge 2. Good. Keep going. Then over constant,
Maybe distance squared.
4 pi epsilon 0. Those are all constant. What else matters? The Q1 and Q2 is the amount of the charge that matters, influence the potential. What else matters? Is the radius, right? Or we call it distance. That's what we learned from the physics. The Coulomb potential definition is Q1 times Q2 divided by the constant and then inverse proportional to the we say R. It's literally the distance between those two targets. Right, agree? Okay, now if we apply to our, this is a general expression. Now if we apply to, let's say, hydrogen atom, what would be the B? Then we have to think about it. One point of charge is the nucleus. The other point of charge is that electron, right? So let's say if Q1 represents the nucleus in the hydrogen, you will have proton that carries the positive charge. Now, how many protons do we have in the hydrogen atom? How many protons do we have in hydrogen atom?
Just one.
And carry one positive one charge, and then the exact amount is E. E refers to a fundamental charge. So therefore, for the proton, it carries one fundamental charge. It's positive. Okay, now how about the electron? The electron is carry a negative charge, carries one negative charge to figure out the total amount is E. That is your fundamental charge. What is the value for the E here, guys?
(1.6 times 10 to the negative 19).
Is that what on the board?
Oh, yeah.
The fundamental charge referred to that's is how much Coulomb. It's 1.60 times 10 to the negative 19. So we just simplify and say one fundamental charge is really 1 times this and get the exact Coulomb value. All good? Okay, now we need to divide it over either 4 pi epsilon 0 and R. Okay, now we can combine the numerator right here. So positive E, negative E, and times E. Then what you have is E squared over 4 pi epsilon 0 and R. Okay. Now, this is a negative sign. So we have, say, when you have energy has a positive or negative, that is because today is awfully quiet. I don't know if it's a light. You know, maximize the light as much as possible. Okay. Oh, is it too bright for you guys?
Yeah.
Yeah, too much.
I can see it.
Right, the energy has a negative and positive sign. The sign refers to the type of interaction. If it's a negative, it refers to the attractive interaction. If it's a positive, that means it's a repulsive interaction. So if you can think about an electron in a positive field of the nucleus, it experiences an attractive force interaction. Okay, all right, very good. Now, I want to bridge one more time. I said hydrogen-like. What if this is a helium plus? You know, instead of hydrogen atom, I will have a one electron system, but in terms of ion, like a helium plus or lithium 2 plus, right? That's one electron system too. So So let's say I have this, let's just say I have a helium, lithium 2 plus. Lithium has 3 electrons, losing 2. That is also 1 electron system. And I'm interested in this guy. What would be the potential energy? Then the one party is always the same. I have one of the electrons. One of the point charge is that electron. Right? The electron only carry 1 negative charge, 1 negative fundamental charge. But now how about the nucleus here?
3.
Huh?
3.
3? Very good. It is 3, right? Because it is a lithium. It has atomic number. We use what symbol to refer atomic number? In your Gen Chem or any classes you're exposed to? Like if we say atomic number, we say nucleus, we use N, electron use atomic number, we use what letter? Typically we use Z to refer to atomic number. Okay, now the atomic number for lithium is 3. How many protons do we have? 3, the same as your atomic number, right? So therefore, I couldn't just use it as a positive Z times that fundamental charge. So if I do an extrapolation for any kind of hydrogen-like system, which refer to 1 electron atom or ion, then the potential energy is a negative sign. It's a Coulomb potential between that 1 electron versus the nucleus. Now, the nucleus, the charge on the nucleus varies, depends on what ion you're looking at it, but it carries the charge of atomic number times the fundamental charge E. So I can make this generic. You guys follow me, okay? Now the lithium is 3, so this will become 3E squared. But what if I have, just like I said, how about sodium, 10 plus? Then the only thing different, this Z would be 11. Okay, now for the hydrogen, the atomic number is 1. So therefore, that's what we have it here, is a negative E squared instead of anything else. You guys follow me, okay? All right. So therefore, we can put it here, E squared. Now we can complete this equation. The 1 electron hydrogen atom Hamiltonian operator will consist of kinetic energy plus the potential energy. In the system, we have 2 particles, so therefore the kinetic energy will have 2 components. One defined referred to the nucleus, one referred to the electrons, and then in this particular system, it's in a Coulomb potential, so we have this 1 potential energy term. So therefore, that is your Hamiltonian operator. Now, we can write out more if you guys want me to. So we say we will have this Hamiltonian operator that carries two position coordinates. The Rn refer to the nucleus, Re refer to the position coordinate for the electrons. Now you can span this into 6 x, y, z variables as you wish. Okay, and then what you have is that you're going to have a kinetic energy. We can write out the expression that has a constant h bar squared over the mass of refer to the motion of the nucleus. Then you have the kinetic energy operator refer to the nucleus, and then you have the del squared. All right, do you guys still remember what del squared referred to?
Could use a refresher.
In math, this is we call it del squared. It's abbreviation, but del squared is a mathematical operation. What was this? It's the partial derivative with respect to the x, y, z. All right, so therefore, you can abbreviate it. Or if you wish, you can write out like that, that's fine too, the same thing. Okay, so we only finished the one. That is your kinetic energy operator for the nucleus. Now what else do you have? Then you have the kinetic energy operator for the electrons. Yes, that's the component here. And then what else you have is your potential energy between the nucleus and the electrons. Now, you have a position vector for this guy. You have a position vector for your electrons. This R is really the distance between the nucleus and the electron. But if you know the position for the nucleus, the position for the electrons, you should be able to figure out what the distance is. Okay, so basically, this is a 6-variable Schrödinger equation for the Hamiltonian operator. All right, now how many of you guys solving for 6-variable in your math? It's very, very challenging. Okay, because solving an equation, this is a mathematical function. Hamiltonian operator carry 2 position vectors with 6 variables. Same for your wave function. To exactly solving for this, it's very challenging. Now, what do we do? When you can't do something exactly, what do you do? What do we do?
Approximations.
We do approximation. Who said that? Maybe I heard multiple people say. We do approximation. Now, how are we going to do an approximation, guys? And that's what we're saying. Okay. Now I can bridge it one more time. Okay, let's leave this. I just asked you guys, since you guys asked me like isotope even more crazier than a single atom. Okay, now let's say I have a helium atom. For helium atom, how many systems do we have?
Systems we have.
You have nucleus. It's an atom, you have a nucleus. What else does the helium atom? Helium has how many electrons?
2 electrons.
So then I have one of the electrons. And what else do I have? Oh, we have the second electron. So therefore, how many position operator would I have? I need to have 9 position operator. You guys agree? Because I will have the position operator for the nucleus, position operator for the electron 1, position operator for the electron 2. Okay, now, can we come up and have a Hamiltonian operator for the helium atom? Let's think about the component. You have a kinetic energy, right? The kinetic energy for the nucleus. And then you have the kinetic energy for the, you don't have to write it down, for the one of the electron. What else?
The secondary electron.
You have the kinetic energy for the second electron. That just describes the motion in X, Y, Z. Now, that's just the kinetic energy component because you have more particles, so therefore you have more things to consider. Now, how about potential energy?
Potential energy between electrons.
Can we imagine this for quantum mechanics for 2 electron system? It's already gets kind of hard. You have a nucleus, you have one of the electron here, you have a second electron here. Now think about it. Now think about the Coulomb potential. When you have a Coulomb potential, point charge, one of the electron to the nucleus, and then you have the second electron to the nucleus. You guys all agree? We never think about to that extent, isn't it? What else do we have? You have electron repulsion. So therefore, to solving for the exact Schrodinger equation, even 2 electron system is already a question. Not to mention, we look at the atom have more than 2 or 3. So therefore, thinking about solving things exactly, that's not going to happen in quantum mechanics. A lot of time we're taking approximation. Are you guys all following okay on this? Now, doesn't mean it's not good, it's beautiful, but we need to be smart doing what we like to do. Okay, so the approximation we're going to take how many of you guys watched the Oppenheimer movie? What is his contribution? I mean, he was credited as the father of the hydrogen bomb, right? Credit. He was credited as the father of the hydrogen bomb. Who watched it? Oh, okay. What do you guys think about the movie? What do we credit him to?
He did a lot of the calculations.
Leader.
Huh?
He was the leader for the Manhattan Project.
He was a leader for the Manhattan Project. The U.S. want to develop strong weapon for massive destruction, right? To end the war, whatever, with the army military purposes, right? Now, at the time, you could have this typical weapon, but not strong enough. So they were thinking, based on what they learned about from quantum mechanics and the field of hydrogen, how the energy release and all of those, and nuclear material, they were thinking they can develop something more massive, better, stronger, more intense. So he actually literally organized this group of scientists from many fields, including chemistry, physics, right, engineer, all together, just like you guys said, lead the Manhattan Project. But he himself is a theoretician. Okay, but he worked with a nuclear chemist because you need nuclear material to develop those weapon. You need those material, but to design how much energy going to output and so on and so forth, related with a lot of theoretical component of the work. They decided to choose that one, tested it something somewhere new, people don't know, and that's where the Los Alamos National Lab, the origin of, because that's in the middle of nowhere, right?
Nowhere in
You know, I work at the Oak Ridge National Lab for a couple years, and that is also, you guys know that Oak Ridge National Lab also was not on the map during the Manhattan Project. It was not. The lab was there, but they didn't put on the map because it's all secret. Because it's involving not just the Los Alamos National Lab, but also Oak Ridge as well as others, because that was the place they dumped the residual stuff for the nuclear and all the warfare remaining stuff. You know, when I work at the Oak Ridge National Lab, I'm a foreign national. They have Y-12 plant. They call it Y-12 plant. It is related with the nuclear material, but I can't go visit. I would love to see what that plant looked like, but I can't. It's still to this day is a secret. Okay, so I digress. He was credited with the invention or the development of the bomb, but actually it's a collective effort. He was just leading it, right? I mean, he has a great leadership. But if you read the textbook, there's a called the Oppenheimer approximation. Oppenheimer approximation, that's what we're going to talk about it. What is approximation? What we're going to say, instead of we have a coordinates at any, you know, in the XY dimension, what we can do is we can put the nucleus as the origin. Which means at the 0, 0, 0 point in this axis. And then, instead of considering the motion of the whole thing as a whole, we only consider only the relative motion, right? Because I said you have a hydrogen atom, you have the nucleus and the electron, they're all moving and they experience this Coulomb potential, you know, it can be challenging. That's a 6 spherical problem. Now, if we reduce it, what if we say the nucleus is actually stationary? We only consider the motion for the electron moving around the nucleus. That would simplify the problem. Why is that? Because if you think in that case, then you can put the coordinates on the nucleus, that's your 0, 0 origin point. Then whatever the electron is, right here, then you have only the one coordinate for that electron. You guys follow me, okay? Okay, if that is the case, okay, first of all, can we do approximation all the time? It's like you guys, you know, I don't have money, I want to borrow from Jordan $1,010. I say, Jordan, I don't have money. I know you're rich. Can you give me like 1,010? And then I was like, okay, can we approximate it? You know, 1,010 is just equal 10, right? So I just give you back 10, and we are just squared fair. I don't think you agree with me. I do. I will agree with that. So therefore, when you do an approximation, it has to have justification. Right? It has justification. Now you can think about it. Let's think about the mass. Let's think about the mass of the nucleus. Let's just using a hydrogen atom as an example. What scale? what value roughly for the mass of hydrogen
Oh,
nucleus on what kind of order? 10 to the
-27.
negative 17?
17th? Oh, I'm thinking of electron. What is it?
27?
Oh,
Oh,
yeah,
that
sounds-
one I'm not entirely sure.
An electron weighs, is it?
What
10
is
to
the mass of
negative
proton? What is the mass of proton, guys?
10 to the negative 27.
Okay, 10 to the negative.
Yeah.
Alright, now how about the mass of the, this is a proton. On that order, okay? Then what about the mass for the electron?
10 to the negative 31st.
Okay. So therefore, it is orders of magnitude differences. So your nucleus is so much bigger, the mass, than the electron. So you could consider it is as stationary when you refer to the motion of the electron. Are you guys following me okay? Okay, all right. Now, if that is now this is our model. We're looking at the hydrogen-like system, but we only consider the motion of the electron with respect to the nucleus. If that is the case, then what is our Hamiltonian operator? Then our system right here. So under this model, what is our system, right? Our system really refer to the what?
Motion of the electron.
To the electron now. Do you guys agree? Because we only understand the motion of the electron with respect to the nucleus. So you can approximate it just that electron. So in that case, we only need a one position operator. It's about time.
Mm-hmm.
No second to spare? Okay.
No
Then we can talk about